Hi, in the previous lesson we have looked at Java literals. In current lesson we are going to revisit primitive data types. Okay, let's recap what we have learned in literals class. Integer numbers are two types, we have integer literal and long literal. Also coming to floats, we have float literals and double literals. We have looked at Boolean literals, true and false. Also we have looked at char literals, which will be included in single quotes. Okay, also we have looked at some escape sequences. That's what we saw in previous lesson. Also we have learned literals can be separated by using underscores for readability purpose, and we also looked at different kinds of systems like decimal system, hexadecimal system. So that is all about literals. Coming to primitives, we have already covered primitives and we looked at primitives so many times, but in this lesson I am going to get technical. So you are going to see some of the things for the first time. For example, in the previous lesson I said 20 billion is not a valid not a valid integer literal, but it is a valid long literal. We will see all those things. Previously we know those byte sizes. Now we are going to look at actual values. Okay, let's get started. In our primitive discussion, the first one is a Boolean, which is a easy one, and it has only two values, true and false. So that is all about Boolean. Then coming to whole numbers, we have byte, short, int, long, and we know they will occupy 1 byte, 2 bytes, 4 and 8 bytes in the sequence. So 1 byte is nothing but 8 bits, and 1 bit can have either value of 0 or 1. Okay, being said that, we have both negative numbers and positive numbers. So the first bit is saved for this minus or plus value. So to know the whether it is a positive number or negative number, it will be coded using the first bit. So to save that data, actually we have only 7 bits. So we can save 2 to the power of 7 values. That is nothing but 256 values. From minus 128 to 127, we have a total of 256 values because there is 0 in between. So there are total 256 numbers. Okay, let's look at byte in more detail. Okay, so as I said, we are going to have only 7 bits. Even though 1 byte has 8 bits, 1 bit is reserved for positive or negative sign. So we have only 7 bits. Using those 7 bits, these are the various values that you can represent. For example, all zeros, it will be its value in decimal system will be 0. So by flipping first bit, you will have 1. So we will go on like that. Okay, these are the different values that can be represented using 7 bits, and each bit can be either 0 or 1. For example, here if you see 127, this is a decimal system number. So how do we got 127? So this is how we got. Actually, this one is in 10 to the power of 2 place. So 1 into 10 to the power of 2 plus 2 into 10 to the power of 1 plus 7 into 10 to the power of 0. So that's how we got 127. So for example, here its value in decimal system will be 10. How it is going to be? So the first one is in the third place. So 1 into power of 2 comma 3, that is nothing but 2 to the power of 3, and 0 into 2 to the power of 2 plus 1 into 2 to the power of 1 plus 0 into 2 to the power of 0. It's going to be 8 plus 2, that is 10. So the maximum value is 127. It is going to be all ones except for the first bit. Its value is 127. So a bit can say a byte can save only a maximum of 127. Okay, here if you see, I have created a byte variable and I am assigning 127. But in the previous lesson, did I say we have a byte literal? I did not say that, right? We don't have a byte literal. We have integer literal. So this is an integer actually. This is not a byte. 127 is an integer. But because the compiler knows that byte can hold 127, it is allowing us to write 127 or assign 127 to this byte variable. Let's change it to 128. Okay, so if you see the compiler error, you can clearly see that possible lossy conversion, meaning there is going to be loss of precision or data, okay, loss of value from into byte. So you can clearly see that it is trying to convert from integer to byte, and because byte cannot hold 128 because the maximum value is 127, the Java compiler won't allow you to assign 128. So the maximum value you can assign is 127, but if you want to assign a negative value, you can assign 128. You will see some you may think that there is some asymmetry, because on the negative side you are seeing 128, on the positive side you are going to see only 127. That is because 0 is considered as a positive number. So 0 to 127, that is nothing but 128 numbers, right? Minus 1 to minus 128, that is 128 numbers on the negative side. So total 128 negative numbers and 128 positive numbers, which includes 0, is we have total 256. That can be saved in a 7-bit binary number. That's okay. So coming to short type, we have 2 bytes. So as I said, 1 byte is 8 bits. So 2 bytes is 16 bits. Out of those 16 bits, 1 bit is required for reserving the sign, either minus or positive. So we have 2 to the power of 15 numbers, right? So this is the value. So the minimum negative value will be 2 to the power of 15, and maximum positive value will be 2 to the power of 15 minus 1, same as this one. Okay, so the maximum value we can represent is 32,767. So that's what I'm assigning here. If I change it to 32,768, again, I mean, we have seen this concept already. This is a int literal, so it is a integer. We are trying to assign integer into a short. Okay, so short data type cannot have this value, so it is going to it is going to complain. So let's change it back to 7. Now we are moving to integer 4 bytes, so 32 bits. 1 bit goes for sign, so we have 31 bits for representing the number. So the range is from 2 to the power of 31 on the negative side, on the positive side 2 to the power of 31 minus 1. Okay, I'm going ahead with long also. Long 8 bytes, so we have 8 into 4, that is 8 into 8, that is 64 bits. 1 bit goes for sign, so we have 63 bits. So the range is 2 to the power of 63 to on the negative side, and positive side it is 2 to the power of 63 minus 1. So this is a very, very big number. So generally this long will be sufficient to represent very astronomical numbers, meaning very, very big numbers. But when we go to some probabilities and lottery winning kind of thing, the numbers we need are more than this. In that case, we are going to see we have some big integer and big decimal. That time we are going to see, but for now see that long has a very big value, and whatever big value we need generally can be accommodated in long. Okay, so this is maximum integer value. If I try to give, so it is int literal. So the moment I change it to 5, what happened here? 2147 483 647 647. Okay, this is a maximum number, right? 647. If I change it to 8, so it is an integer literal, but integer cannot represent this number. This is 1 more than the maximum value. So if you see now, the error message is different, right? Integer number too large. So this cannot be an integer literal. So either we need to make it long literal and assign to long, or be happy with ourselves with a value of this around 2 billion value. So whenever you need some value more than 2 billion, you have to go for long. Okay, remembering this value is very difficult, but just remember it is around 2 billion, and if you need a value that is around 2 billion, the chances are you should go for long. Okay, that is all about the ranges. We have 2 literals, integer literal, long literal. Compiler is allowing you to assign a integer to a byte or short because it knows the range, but if you cross that range, it is not going to allow you to assign a integer to byte or short, because they can hold very, lesser values. That is all about these 4 data types in detail. If the way the negative numbers are saved is in 2's complement, but I am not going to cover that because that is even more technical and we don't need to know how it is actually saved. Okay, binary 2's complement, that is what they use. Okay, let's move on. Lot of scrolling. Okay, characters. So this is what we have seen in the previous lesson, right? Characters can be included in single quote and can be assigned to variables of char type. But here the thing we need to understand is char is having 2 bytes. So previously we have seen that 2 bytes can include around 64,000 numbers, right? 64,000 different values. On negative side 30 something, and on positive side if you include, they can hold around 65,000 values. Here when we come to char, it is unsigned, saying all the numbers are positive only. So we don't need a bit for representing either number is positive or negative. So we can use all the 16 bits. So the range is from 0 to 65,536. So when Java started, this was more than enough to represent all the characters that are available in the worldwide. The number of characters that are encoded using UTF-16 were less than this one. So Java started with that. But after that, many Chinese characters, Chinese words, they all are included in as characters. And now this 65,536 is not a enough value to save all those characters. We have more than these many. We have more than 65k characters. So what happens is UTF-16 encoding uses variable length encoding. So what do I mean by that? Let's go to Google, our friend, and search for UTF-16 encoding. Okay, if you see here, generally all the values that we generally use from day to day, they can be represented using 2 bytes. Like they can be saved in single character. For example, it can be saved in a single character. Okay, so because its value is 00641. Okay, so from 0000 to 00FF, right? Sorry, not 00FF, from 0000 to FFFF. So whatever can be represented, they can be saved in single character. But if we come down, see, this is a I don't know whether it is Chinese or really I don't have any idea, but it cannot be represented in FFFF. It is more than that. Okay, so they use a different encoding technique to convert this 10437, where is that, so into 2 different bytes. So 2 different codes. So these are called code units and this is called code point. So in Java, okay, in Java, every character, I am not talking about char data type, I am talking about character. Every character is encoded using code points. Okay, so some code points, for example, dollar symbol, this needs only one char, like this one, right? This can be represented only using one char, nothing but this one, right? Because it has 2 bytes, it can save 002400. This value can be saved there, here 0024. Okay, so dollar can be saved in single character. But coming to this Chinese character, it is still one code point, but it has 2 code units. If you see, this is the total code unit. Okay, I'm sorry, Okay, so how do I save it? Okay, I need two chars, not single char. Okay, so char c11 equal to, okay, so that single code point which has two code units need to be saved like this. So what did we understand? Java uses 2 bytes to save a char, and it uses UTF-16 encoding. UTF-16 encoding is of variable length encoding. What do I mean by that? Some characters just need one code unit. Some characters needs two code units. Okay, so whatever code units that can be represented, whatever characters that can be represented using one code unit can be saved in a single char, but whatever code points, not code points, whatever characters that needs two code units need to be saved in two characters, not a single char. Okay. Yeah, so this is very confusing, right? So okay, how can we say this is first code point of a code unit that, I'm repeating, how can I say whether it is a single code unit of a single character or the first code unit of a character that needs two code units, or other way of saying, whether it is representing complete character or it is only representing first code unit of a character. So how can we say that? So the encoding technique is very intelligent. I mean, the way they are encoding is very intelligent. So if it is falling in this range between D800 and DBFF, then this is the first code unit of a character. First code unit of a character. Okay, if it is falling in DC00 to DFFF, see DC, then it is second code unit of a character. So there is so much technicality involved here because it is using a variable length encoding. So by looking at a char, we don't know whether it is a complete character or part of character. So our char data type is not sufficient to represent a character. That's what I want to drive at. A char data type is not sufficient to save every character. Some characters can be saved using single char. There it is fine, but some characters cannot be saved in a single char. Okay, so don't deal with char unless you have to. Use strings. Okay, that is the safest way to go ahead and use. Unless you know the encoding, unless you understand code points, code units, variable length encoding, don't go for char, because char is at very low level. It is not able to represent a character. Some characters it can represent, but not all the characters. Yeah, I will ask you to go through this link and read a bit more so that you can understand. That is about char. Okay, it is very technical. That is the reason I did not cover all these technical details when I introduced the primitive types. They are very technical and you need to understand many things to properly understand character. That's okay, but we learned our lesson. Unless we know what we are dealing with, don't use char. Okay, that being said, we are moving to floats. These floats are even more difficult to understand. If you concentrate, you can understand UTF-16 maybe in half an hour, 1 hour. If you need more time, maybe maximum 2 hours. And floating points, you are going to take more than that. Okay, this is one good link to start learning about floating points. Okay, so floating points are explained here. James Gosling. He is the one who introduced Java along with his colleagues. He says 95% of folks out there are completely clueless about floating points. So majority, 95% is not a small number. Okay. So so let's try to understand what we can understand about floats. Float is using IEEE 754 encoding to save the floating point numbers. Okay, the minimum, this is a scientific notation. Okay, so when we say minus 45, you have to go minus 45 places to the left. When it is plus value, you have to go, you need to go 38 places to the right. Okay, so this is scientific notation. For example, let's take a simple example. Okay, float 1 equal to I can write through 345 dot 22345. Let's not get confused. Let's write 123 dot 456f. Okay, I can write this, or I can write float 2. Let me move it to the left side. In that case, it will be 2f. What is happening here? Okay, I missed E. So basically, when you see plus 2, you have to move to here, because it is going to be multiplied with 10 to the power of 2, that is 100. So these two are equivalent. Those two are equal. Other way of representing this one is, let me move right side, and in this case I have to write minus 2. Okay, so this is how we represent. These are very big numbers. Okay, but here the important thing to note is float has only 6 or 7 bits significance. Okay, it has only 6 or 7 significant decimal digits. Okay, what do we mean by that? Okay, I will explain that, but let's understand more about floats. Floats are nothing but fractional parts, right? How many fractions are there between 0 and 1? There are so many, like 0.1, 0.11, 0.111, 0.1111. So you can go on like that. Okay, between 0 and 1 there are so many fractions, so it has to represent even bigger numbers, right? Like 123. So between 123 and 124 there are almost infinite number of fractions. So how will float represent all those characters? It has to sacrifice some of the accuracy it has. What do we mean by that? Okay, let's see what we can represent and what we can't. First thing we want to do is, it has a 6 to 7 significant decimal point digits. What do we mean by that? First, let's consider a int. What? Okay, I am going with simple ones. Int 1. So let's say 1 2 3 4 5 6 7. Okay, let me assign it to float. Okay, float 4 equal to, I'm going to assign that integer value. Let me print this float value. Okay, we want to print float 4. Okay, let's see. I assigned 1 2 3 4 5 6 7. It is running. Yeah, we got 1 2 3 4 5 6 7.0. That's good, right? Okay, let me do a different kind of printing using printf. So what it will do is, it will use a format specifier. So in this case %f, because I want to print a floating point number, but I can tell it how what is the length and how many fraction parts I want. So if I print this is good. It is very good. I mean, it is able to represent this value accurately, right? So let me increase the length. I mean, let me do it 22 and 21. Let's see what happens actually. Okay, so it is able to represent this value very accurately. Okay, so let's change it to 1 2 3 4 5 6 7 8. This is good. 9. This is okay. Now the problem came, right? I assigned 1 2 3 4 5 6 7 8 9. Please be patient with me, because you need to understand this. I have assigned a value of 1 2 3 4 5 6 7 8 9. What happened is, I got 1 2 3 4 5 6 7. Where is 8? I mean, instead of 8 it saved 9 2. So it lost significance, right? I mean, it lost the precision. It is able to accurately represent up to 7 numbers only, not 8 onwards. When I gave 8 9, it is printing it is printing 9 2, right? What was that? 9 2, because it can't accurately represent this number. It doesn't have those many bits to represent this number. Okay, so it said 6 or 7, then why did I go till 9? Okay, let's confine ourselves to 8 characters and prove that it cannot save this number. Okay, but here I am not able to prove that it cannot save properly. Let me change it. I know what I need to do. Let me save 0 0. Let's try now. Wow, good. 21. So for some reason it is able to save. I mean, previously I tried with some number, I don't remember. Okay, 7 1. Let's try this one. Okay, it's doing something good. Okay, but we have seen that maybe let me try in a reverse order. 8 numbers. 8 7 6 5 4 3 2 1. See, I gave 8 digit number. Okay, 3 2 1. Instead of 3 2 1, it started printing 3 2 0. It lost the precision at the eighth number, right? So it can represent only 7 digits with precision. So that's what they meant by with 6 or 7 significant decimal digits. Okay. Okay, so if we see for double, it is going to be the same thing. It up to 15 decimals, up to 15 numbers it can represent, but after 6 when we touch the 16th one, it is going to lose that precision. Okay, accuracy actually. I hope you are satisfied when I said it cannot represent 8th significant decimal number, because here you are able to clearly see I have given a number with 8 digits and it is not able to represent that. Okay, so let's see one more thing. Okay, like let's try to assign float 5 0.1 to this float value, and let's print it. This time you are going to be surprised, and you won't believe what you are seeing. Okay, let me use \n here, so they will be printed on different lines. What did I give? I gave 0.1, but what did it save? It has saved 0.1. After that, it has significant. I mean, it is very accurate up to 7 digits, but after that what happens is it will save some other numbers, because in floating point we cannot save 0.1 accurately. Okay, for example, in decimal system, when we say 1.1 by 3, okay, in decimal, how do we represent 1 by 3? We will say 0.3333 up to something, right? After that, even there are so many 3's there, but we cannot accurately represent it. So in floating system we cannot represent 0.1. So that is the reason when if you compare 0.1 to 0.1, it may or may not be true. Let's check that. Okay, Boolean compare floats. equal to, okay, we will take 0.1. Is it equal to, this we will see later because we haven't covered comparison operators, so I don't want to give those kind of details at this time and confuse you. But please know that 0.1 cannot be represented in floating points, and don't compare floating points in whenever you want to see whether they are equal or not. For example, 2, if you check 2 with 2, it will be always true. Okay, for example, if you do 4 minus 2 double equal to 5 minus 3, because it is going to be 2, it is going to be 2, right? It is always going to be true. They are always going to be equal. But if you do the same thing like 0.3 minus 0.2, if you compare this value with 0.1, it may or may not be equal. Okay, most of the times it won't be equal. So you will be surprised to see why they are not equal. Okay, so the main point you need to understand after saying all these things, floating points, they have round off errors. What do we mean by that? Because they have so many digits at the end. If you add 0.1 plus 0.1, it is not going to be 0.2. It is going to be 0.2. After some 6 or 7 zeros, there is going to be some other value. So that is what happens. So floating point numbers never save any values that needs that kinds of accuracy. Okay, it is not going to be accurate. The floating point cannot represent the numbers accurately, and there is going to be round off errors. Double is a bit better because it can represent up to 15 significant digits, but even then double also has some problems of its own. Unless you need to use that, don't use. Okay, whenever you are doing some financial calculations, and if you need lot of accuracy, don't use these two. Then what shall we do? we have a big decimal, we can use that. I will cover that big decimal in a different lesson. Okay, I believe I have taken so much time. Okay, but I wanted to explain these things, their seriousness and our misconceptions. Okay, let's go ahead and review once again. Okay, so Boolean true and false were good. Whole numbers, byte, short, int, long, they can have only these values in this range, and this is always integer literal. When the value can be saved in byte, the compiler will allow. Also this is not a integer literal, because integer cannot have this value. Okay, long literal will be having L, that we have seen. We have looked at some binary representation of numbers to understand the maximum value we can have is 127 for a byte. Then we moved on to char. We saw 2 bytes and it is unsigned number, so we can have up to 65k numbers. And with modern languages and their characters and all those things, a single char cannot represent all characters. Some characters it can represent, but some characters it cannot represent. To represent those kind of characters, it needs 2 chars. Okay, because those characters has a single code point which has 2 code units. Okay, that is about char. Unless you know what you are dealing with, don't go for char, simply go for strings. We will cover strings later. And go ahead and read this so that you will have more understanding. We moved to floating point number. I gave you a link to go through and understand about floating points. Then we have seen that floating point has only up to 7 significant decimal numbers, or 7 significant digits. We have proved that by assigning a value 87654321, which it is saving as 87654320. Also we have seen that it cannot represent all numbers. For example, 01, it is saving as something else. The easiest way to remember that is, in decimal we don't have a proper representation for 1/1/3. We will write 0.333, but we cannot go indefinitely, or we cannot represent all infinite threes there. So we have to stop somewhere for accuracy purposes. So we do the same here also. So whenever you are comparing floating points, be careful, because they may not be equal. They may look like equal, but they are not, because there are some other fractional numbers at the end, so they will cause them not to be equal. Okay, that is all about primitives, long lesson, so many details, so many confusing details, so much complexity. But uh, in general programming, we always use int whenever integer is required. We generally go for long only when such a huge numbers after 2 billion is required. In decimal system, in floating points, we go for double, because we have seen the 7 significant digits are not sufficient for regular calculations, so we don't use float unless we have to. We generally go for double. When financial accuracy, like 2 cents accuracy, 3 cents accuracy is required, we go for a big decimal, that we will cover later. But remember, int, double, be careful. Thank you for watching this video. Happy learning. Please subscribe and share it with others. Thank you.